In example 4, we have a really cool function that is also really cool to differentiate. So this one's going to be a lot of fun. We're going to analyze the behavior of this function, which is x squared times 4 minus x all raised to the third power. We want to use calculus, so we're going to find the critical numbers, then make our sign chart and see where the function is increasing or decreasing based on the sign of the derivative. So on first glance, looking at this function here and thinking about how to find its derivative, you have to be a little careful because what we have here is a product of two things, and each of those two things involve x. When that is the case, you definitely want to use the product rule 100% of the time. That's not true. If you wanted to, you could also expand this out, cubing this and everything, but that will be the longer route to take, and it actually will make the problem harder for you when we end up trying to factor the derivative. So I know that we tend to forget the product rule sometimes. We get a little too excited about finding derivatives, and so here's just a meme over here about how that might feel to the product rule when you forget to use it. I know it's tempting to differentiate each piece, but we have to, calm ourselves and just make sure that we respect the rules and the functions and the derivatives. So I think that we want to use, how about u and v, right? That's what we normally use to talk about things in the product rule. So I'd say like we've got u equals x squared. Then we've got v equals 4 minus x to the third. Maybe let's just note here, right? We need the product rule. So in the product rule, it says we take the first times the derivative of the second plus the second times the derivative of the first. We need the derivatives of each of the individual pieces. So u prime is 2x. And to find v prime, we're going to need the general power rule. We'll bring the 3 down and multiply, subtract 1 from the power, and then the inside's derivative is -1. Right, 4 minus x, so we've got a -1 derivative. Just simplifying this one step, we'll multiply the 3 and the -1, but I'd leave the 4 minus x squared there. All right, now putting this all together, we'll have u times v prime, then plus v times u prime. Now, we are going to want to find the critical numbers of this function. That means we're going to want to set this equal to 0. We're going to also find where it's undefined, but that actually won't apply in this case because we don't have any denominators. But setting something equal to 0 is a situation where you want to factor 99.99% of the time. So simplifying this is going to be really helpful for that. So there's a lot of parentheses within each of these things across the plus. So we're going to just work individually with this part here and this part here. So in the first part, I would multiply the x squared and the -3, and just write that as -3x squared, and then parentheses 4 minus x whole thing squared. And it just looks a little bit easier to handle when it's written in that way. And then in the second part, we would write the 2x in the front without the parentheses. And again, that looks just a little bit better. Now within each of these blue blobs here, they haven't changed, but now what we want to do is write this thing that's a plus here as a product, like the whole thing as a product. And the way to do that would be to factor out a greatest common factor, or a GCF. Again, we're only doing this right now because we know the goal is going to be to set this equal to 0. So whether you set it equal to 0 before you factor or after, doesn't really matter. Okay, so our GCF, we're going to look at the numbers in each of the blue blobs. There's nothing to pull out there, but here we have x squared and x. So we could take out an x. Then we also have a 4 minus x squared and a 4 minus x cubed. So we could take out a 4 minus x squared. Okay, so here is the GCF. Now what's left over in the first blue blob here will be a -3 and then an x to the first. Then in the second blue blob, we've got a 2 left over. We took out an x, but we have a 4 minus x to the first left. All right, we've got it factored. It's a product of 3 things. But within here, you can simplify this a little bit further because if you think about just distributing the 2 into here and here, you can combine some like terms together. When you distribute the 2 into here and here, you'll get a -2x, and we've also got -3x, so that's -5x. Then we've got +8. And there it is. There's our beautiful derivative fully factored into a product of 1, 2, 3 things. Okay. So now we want to set this thing equal to 0 to try to find our critical numbers. Okay, so f prime of x equals 0. All right, we're going to set the entire derivative equal to 0. We did all of the hard work already. Okay, so now we just get to say, well, hey, with this x here, so when x is 0, that whole product will be 0. This one here, 4 minus x whole thing squared, that will be 0 when x equals 4. And this factor here will be 0 when x equals 8/5, and you might need to do a little bit of work to see that. All right, we're just setting that factor equal to 0 and solving for x. If you don't like the 8/5, you can rewrite that as get a decimal for it. So it'll be 1 3/5, and so that's 1.6. All right, so once we find our critical points or our critical numbers, here is where we want to make a sign chart for the derivative. Okay, so we've got 3 critical points. I'm going to make mine not too tiny. I like to have enough space, but you do want to put them in order. So we have 0 as our smallest one. We've got 8/5 next. And then we've got 4 as our biggest one. All right, so this is going to split our number line up into 4 different intervals. So we've got from -infinity to 0. We've got from 0 to 8/5. We've got from 8/5 to 4. And then we've got from 4 to infinity. Eventually. I hope you know what to do at this point. We want to test some, thank you, we want to test some values within each of these intervals and plug them into f prime. Okay, so we want to test, that's not the best word. How about we want to check the sign or determine the sign of f prime on each interval. All right, so a little bit of calculator work here. Pick whatever numbers that you want to plug in. Make sure that they're all going into the derivative here. Okay, so we want to test some values in each of these intervals. So how about -1? All right, so we want to do f prime of -1. Now here's a shortcut way that you can think about this without a calculator, if this is something that makes sense to you. Since we have a product of 3 things, we can just consider what the sign of each thing is at the number we're testing. So when we plug a -1 in for x here, that'll give us a negative value. Then when we plug a -1 in here, well, this factor is squared. So no matter, I don't care what it is in the parentheses, you're squaring it, so it's going to be positive. So that factor there is going to be positive. When we plug a -1 into here, we'll have -5 times -1, which is +5, and then we add 8. I don't care what number that is. I'm not even wasting energy on thinking about it, but I know it'll be positive. And when you multiply negative times positive, the outcome of that is going to be negative. Maybe I'll just stick with my colors here. So negative, I think, was green. Okay, so the derivative for -1 will be a negative value. So you can try this for the other intervals too. So we could test something here like, how about 1? Because I know 8/5 was 1.6. So when we plug a 1 into the derivative, okay, the first factor here, the x, that would be positive. That second factor is always positive because it's squared. And when we plug a 1 into here, we'll have -5 times 1, which is -5. And then when we add 8, that's going to push that over to be positive. Okay, and so overall here, this product of 3 positives will end up being positive. All right, we've got 2 more to test. How about x equals 2 here? When we plug a 2 into the derivative, the first term will be positive. The second term will always be positive. And now the third term is going to end up being negative because we'll have -10 plus 8. Okay, positive times a negative is a negative number. All right, so we've got a negative sign for our derivative on that interval. One more here, bigger than 4, so how about 5? F prime of 5, when we plug that into the first term, just the x will have a positive value. Here, when we plug a whatever in here, that's positive again because it's squared. And when we plug a 5 into here, that will also be negative. -25 plus 8 is a negative number. And so overall, when you multiply positive times negative, you'll get a negative value out. Okay, a little tedious, but not too hard, right? So let's make our conclusion. Interpret the calculus for everyone else who isn't fortunate enough to understand what this means. So let's see, our original function, which was x, what was it actually? X squared times 4 minus x cubed. Okay, it's increasing wherever the derivative is positive. That was just on that one interval from 0 to 8/5 and decreasing on the rest. So -infinity to 0, union 8/5 to 4, union 4 to infinity. So let's take a look at what this function looks like. Just double check our work. So again, pull out your graphing calculator or go to desmos.com on your phone or your computer and let us plot our function this time. So we had x squared, then it was 4 minus x, and that was raised to the third power. Okay. Let's just get a, I don't care like how steep it is or anything at this point. I just want to get a sense of the shape of it. So it's one of the cool things about Desmos on your phone is you can kind of pinch it and move it around and don't have to mess with windows or anything like that, like on your calculator. But you should not be using Desmos for your exams or your quizzes. You should be using your calculator, so make sure you know how to do it on your calculator. So let's see, let's kind of, what numbers have we got here? It looks like we've got zeros as a turning point. Between 1 and 2, there's our 1.6 or 8/5. And then at 4, we've got, looks like a horizontal tangent line, but then it continues to decrease. It doesn't turn around there. So let's sketch this into our notes and see. I think that's what we found here. Here is Dwight from The Office just saying that calculus is basically algebra, which isn't quite right, but there's a lot of algebra in it. Okay. So there's just more going on over on that side of the y-axis. So I just kind of wanted to make that side bigger. So it's doing something like this, down, right, then it went up, then it went down, and then it didn't go up again, it went down even more. So there's our function. Let's just sketch in the important numbers we found. Our critical points were at 0. Here, this was 8/5. Okay, here's at 4. Notice at all of those 3 places, we've got a horizontal tangent line or a slope of 0. The function turns around at 2 of those, but at 4, it continues to decrease, right? And so that's kind of what we found in our chart, right? So the function is decreasing till we get to 0. Then the function increases from 0 to 8/5. Then it decreases from 8/5 to 4. It's 0 there in its slope for a point, and then it continues to decrease. This function is so cool, and we just analyzed the heck out of it with the first derivative. There are more things to analyze about a function, as we will continue seeing in this chapter. So tune in. I'm excited to share that with you, and I hope you have a great day.